Good morning. Welcome to another session with me, Sri Lekha, lecturer in mechanical engineering. So, till now we have discussed something regarding the centroids, and but we have also discussed the problems on uh, symmetric sections and I section, C section, and certain laminar areas with cutout portions. And in today's class, we are going to discuss something regarding the uh, moment of inertia of various standard sections, right? So let us start, and today's contents are moment of inertia and its concept. So what actually moment of inertia is will be discussed, and how would you apply that moment of inertia for a rectangular section or a hollow rectangular section or a circular section, hollow circular section. All those will be discussed now. And next, theorems, parallel axis theorem and perpendicular axis theorem. So parallel axis theorem is used when there are two parallel axes. How would you find the moment of inertia about particular axis? And perpendicular axis is when there are mutually perpendicular axes. If two are perpendicular to each other, then how would you find the moment of inertia about the third mutual perpendicular axis? Next, how will you calculate the moment of inertia and radius of gyration will be discussed in this particular class. Okay, so what actually moment of inertia is? So it is simply the inertia is nothing but the property of the body to continue in its state of rest or a motion, right? So in a straight line. So for bodies in the linear motion, the force required to change its state of position will depend upon its mass. So as you know, inertia is nothing but either it is rest of or it is a uniform motion. So now the amount of force that is required to change its motion is depending upon the mass of that particular body. Next, so for bodies which are in a rotation about an axis, then the force required to change the state of motion will depend upon the mass of the body, distance from the axis, and mass of the body and distance from the axis. So previously it was only mass of the body in case of the linear ones, whereas in the rotational ones both the mass and the distance. Right, so now, so mass and surface area are the important design point of views. Now distribution of these parameters and orientation with respect to some reference axis is also important. Nothing but the axis about the rotation and the distance from that is also much more important. Next, so the relative distribution of area and mass with respect to some axis is nothing but the moment of inertia of that body. So simply you can say that moment of force about any point is nothing but the product of the force and the perpendicular distance between the point of application of the force or the body which is leading to the force and the body on which force is applied. So if this first moment of area is multiplied by the perpendicular distance, then the product is called second moment of inertia. Okay, so simply you can say that the moment of inertia of an area is the product of area of the section and square of the distance of the center of gravity of the area from that particular axis, right? So you can see. So this is what the moment of area is nothing but the uh, it is simply the product of force and the perpendicular distance from the distance between the two, right? Now moment, that is nothing but the moment of area or first moment of area. Okay, moment of area, moment of inertia of area is called area moment of inertia. So it is also called as first moment of inertia. It is simply y into delta a. Okay, now so this y into delta a will give the first moment of inertia about the x axis. Now x into delta a will give the next y square into delta a, means y into y square y delta a will give the second moment of area about x axis. Now if you want about y axis, nothing but moment of inertia or moment of area about x axis is simply ixx. So that one you can find by means of ixx equal to y into delta a. Now if I want about y axis, it is Iy equal to x into delta a. If I want second moment of inertia about x axis, then it is Ixx is equal to integration of y square dA. Now second moment of inertia about y axis means Iyy into is equal to uh, integration of x square dA. So if you want y, you need to take the distance from that y axis uh, towards the part where the centroid is acting in terms of x. So it is Iyy equal to integration of x square dA. Likewise, we'll be taking. Next, so what are the various theorems of moment of inertia? First one is theorem of parallel axis, and second one is theorem of perpendicular axis. So parallel axis theorem. So it states that moment of inertia of a plane area about any axis is equal to the sum of the moment of area inertia about the centroidal axis plus the product of the area and the square of the distance between the two axes. Okay, so it is simply that it states that moment of inertia of an plane area about any axis is equal to the sum of the moment of inertia about that particular centroidal axis plus the product of area and the square of the distance between the centroidal axis and the given axis. Okay, so it is simply if IAB is the moment of inertia about the required axis, then if IXX is the moment of inertia from the centroidal axis, then A is the area of the lamina and H is the distance between the two axes. So you can see there AB is an axis about which you need to find the moment of inertia. Now you know that the centroid passes through the point C. So from there also an axis will be there. So that is simply you can say that Ixx is the moment of inertia about the centroidal axis. Now area of that particular figure is A, and let H is the distance between the two parallel axes, that is XX and AB. So now according to our parallel axis theorem, it will be like moment of inertia about AB axis is equal to moment of inertia about XX axis plus A into H square. Now similarly, if I want something about the Y axis, then parallel to Y axis you will have the centroid, and and from that axis you can say there also again IAB is equal to IYY plus A into H square. There H will become the horizontal distance. Here H is the vertical distance and their axis will be vertical, and here we have the axis as horizontal. Yeah. So like this we'll be doing it. Next is perpendicular axis theorem. Okay, so if Ixx and Iyy be the moment of inertia of lamina about mutually perpendicular axes xx and yy in the plane of the lamina, then the moment of inertia of lamina about z axis normal to the plane normal to the lamina and passing through the point of intersection of x and y is given by Izz is equal to Ixx plus Iyy. So it simply states that if Ixx and Iyy are the moment of inertia of plane section about two mutually perpendicular axes xx and yy in the plane of lamina. Now, then the moment of inertia of this section about a zz axis is simply Izz is equal to Ixx plus Iyy. So in this case, you can take simply x as the distance of the piece from the y axis. Now y as the distance of the area from x axis. Now r as the distance of the uh, area from the z axis. Now you can simply take it as moment of inertia x axis as Ixx is equal to sigma dA y square. Similarly, Iyy equal to sigma dA x square, and also Izz is equal to sigma r square dA. Now you know that Izz is simply Ixx plus Iyy. So therefore sigma dA x square plus sigma dA y square. On taking common sigma dA, then it will be left over with x square plus y square. As you know, x square plus y square is equal to simply r square. So hence Izz is equal to sigma dA r square. So this is what our perpendicular axis theorem is. Next, so you know polar moment of inertia, right? So this ZZ axis is known as polar axis, and the moment of inertia about this polar axis is known as polar moment of inertia. So likewise you will be doing it. Now, polar moment of inertia is generally used for finding the torsional stresses. Next, see radius of gyration. So, radius of gyration we already discussed in the previous classes. So, radius of gyration is nothing but the radius of gyration of an area about a given axis is simply defined as the distance with which when squared and multiplied by an area gives the moment of inertia, okay, about the given axis. So you know that I is equal to a into h square. Now if I is equal to a into h square, then h square equal to I by a. Now h is equal to under root of I by a. Now if I am replacing this h by k, nothing but k is equal to under root of I by a. So this k is nothing but radius of gyration. So it is nothing but the distance obtained when squared and multiplied by a given area about the given moment of inertia, moment of area. Okay. Next, so let us find a few standard sections, right? Yeah. So now first let us take rectangle. So the centroid of the rectangle we know already, it is b by 2 along the x-axis and d by 2 along the y-axis. Now you know that area is b into d in this terms if you take b and d. So now we know that centroid is x by 2 and uh, b by 2 and d by 2. We know that moment of inertia is simply I is equal to a into h square. So h square means along the x-axis you have to take the vertical distance, nothing but d square by 4. Okay, d by 2 you have to consider as h, right? Now if I take ixx equal to y square into a. So y is nothing but d by 2. So y square means d square by 4. So area is b into d. Okay. Okay. So like that you'll get bd cube by 12. Okay. So this moment of inertia about x axis is bd cube by 12. Next, moment of inertia about y axis for a rectangle is similarly db cube by 12. So that's what, instead of I equal to, so I equal to db cube by 12. db cube by 12. Next, next moment of inertia about the base AB. So base AB is simply BD cube by 12, BD cube by 3. Okay. So IG plus AH square we have to take. So IG is nothing but, so this is how we'll find the moment of inertia of a rectangle. Simply we'll substitute the values and we take the, we'll do it. So centroidal, the moment of inertia about the centroidal axis, about the x axis is bd cube by 12. Now about y axis is simply db cube by 12. db cube by 12. Next, triangle. Let us consider a triangle. Now we know that for a triangle the area is half bh and Horizontally it is at if you consider x axis, x axis it is h by 3. Now if you take horizontal it is 2h by 3 or h by 3. So now moment of inertia about x axis is bh cube by 36. Next, moment of inertia about base AB is IAB is equal to BH cube by 12. So likewise we'll be doing. So moment of inertia about the centroidal axis XX is BH cube by 36. Now moment of inertia about AB axis is BH cube by 12. Next, circle. For a circle, the you know this for circle it is simply d by 2 from all the sides the centroid lies in. Now if I take ixx equal to iyy, then it is simply pi d power 4 by 64. Okay, so ixx equal to iyy is equal to pi d power 4 by 64. Next, semicircle. So for this semicircle it you can simply take as you can simply take as about centroidal axis as x axis as 0.11 r to the power of 4 or 0.0068598 d to the power of 4 or 0.11 r to the power of 4. Next, Iyy is nothing but Iab here. So Iyy is equal to Iab equal to pi r square power 4 by 8 or pi d power 4 by 128. Okay, so it is pi r power 4 by 8 or pi d power 4 by 128. Next, quarter of the circle. Okay, quarter of the circle. So for this, about the centroidal axis if you take, its value is 0.055 r to the power of 4 or 0.00343 d to the power of 4. Okay, 0.00343 d to the power of 4 or 0.055 r to the power of 4. Next, now let us learn how to calculate the moment of inertia of the given figures. Okay, so just like the moment of inertia, sorry, centroids for the regular figures which we do, say, so first split the entire entire composite section into standard section, that is rectangle or a square or a or a triangle, etc. Next, you need to locate the individual centroids and find the individual area. So individual centroids are nothing but from the x-axis or from the y-axis. For each section, you will find the horizontal and vertical distance of the centroids by making use of the formula like b by 2 d by 2 for the rectangle, and d by 2 for a circle, and h by 3 for a triangle likewise. And areas, as you know, area of a rectangle is L into B, area of a square is S square, and area of a triangle is half BH. So likewise you'll find the areas and the centroids, and we'll fill all the data by making use of a tabular column and the centroid, and we know how to find the centroid of the entire section, that is x bar equal to sigma a x by sigma a, we have done till yesterday. And the y term is sigma a y by sigma a, nothing but moment of areas about x axis by sum of the areas. Similarly, sum of moment of areas about y axis by sum of the areas likewise will do. Now, next we'll calculate the distance between the parallel axis, that is from from their own centroidal axis to the x-axis, or from their own centroidal axis to the y-axis. So let hx be the distance from the centroidal x-axis to the parallel centroidal axis of the each section. Similarly, hy be the distance between the centroidal axis of the entire section and the own parallel centroidal y-axis of each section. Okay, so like this we'll find. So we'll take area of each section and then centroid of each section, and area into the x factor, that is moment of area about x axis and moment of area about y axis. Next, the major centroid. Okay, so major centroid means it is simply the centroid of the entire section. So from there, by making use of that, you can find the distance between the centroid of the section to the major centroid. So that difference is nothing but the distance between the centroidal axis to the centroid of the given axis. Okay, so like that we'll calculate everything. We'll calculate the summation of all the terms. Next, so for each standard section, you need to find IGXI, means moment of inertia about their own centroidal axis. Okay, and IGY, moment of inertia about their centroidal y-axis for each standard section. Next, after that, we'll take area and moment of inertia about their own area, and this is area into distance square, right? So area into the distance square along the y-axis. Similarly, IXX means sum of the ig plus ah square. You know, this can be found, this is nothing but the parallel axis theorem. It is simply the moment of inertia about its own centroidal axis plus product of the area of the plane, area of the section, and the square of the distance between the two axes, nothing but ig plus ah square. Similarly here also, this is moment of inertia about the centroidal axis, and this ahx square is the area into product square of the distance between the two axes. So here if you see IYY means IG along the centroidal y-axis plus A into hx square. So it is simply moment of inertia about the centroidal axis plus this is nothing but the moment of inertia about the uh, this is nothing but the product of area and the product of the square of the distance between the two axes. So likewise we'll calculate. Now next, some of the so some of the moment of inertia about x axis. It will give you. Next, some of the moment of inertia about centroidal y axis. Next, zz is equal to sum of the xx plus sum of the yy. So you know that Ixx equal to Izz is equal to Ixx plus Iyy. So likewise we will calculate all the things. So Ixx can be found by making use of Ig plus Ah square. Next Iyy is simply is equal to some value you will get. Okay, Iyy equal to Ig plus A into x square. So likewise, we'll make use of all the calculations. Next, radius of gyration. So you know radius of gyration k is equal to under root of I by a. Okay, so here under root of I means sum of the ixx by sum of the a you will take. So k equal to under root of ixx by a. So Ixx means moment of inertia about xx axis and Ai is nothing but moment of areas of the summation of the areas. Next, radius of gyration about y axis if I want to find. Is simply kyy is equal to under root of sigma Iyy by sigma ah square. So like this we'll continue. Next, kzz equal to radius of gyration about the centroidal z axis. It is simply under root of izz by sigma a. Okay, so this is how we calculate the radius of gyrations about the centroidal axis. So if you want about xx, then you'll take ixx. If you want about y-axis, then you'll take moment of inertia about y-axis. If you want about the polar axis, z-axis, that is, you'll take about the izz by sigma a square. So let us discuss the summary. So in this class, what all we have learnt? We have learnt the centroid. So centroid is nothing but the centroid center or the point at which the whole area of the body is said to be concentrated. Right? So center of gravity is nothing but the point at which the entire body is said to be entire masses are said to be concentrated. Next, moment of inertia. So moment of inertia is simply it is required for bending of the beams, and centroid and center of gravity are required for equilibrium of the bodies. Next, if a lamina is given and if it is symmetric about the given structures, then we'll take simply centroid will lie about the symmetric area only. Next, so moment of area about given lamina can be taken as second moment of inertia. Now, so this all we have learnt. So again we have learned that Ixx is equal to Izz is equal to Ixx plus Iyy. Next, moment of rectangular section is Ixx equal to BD cube by 12. Next, moment of a circular section is Ixx equal to Iyy is equal to this simply pi d power 4 by 64. Next, radius of gyration is simply KAB is equal to under root of IAB by A. So this is how we calculate all the radius of gyration and all. Now here IAB is nothing but moment of inertia about the same axis. Next, A is nothing but area of gyration. So this is all what we have learned today. So let us once again clarify all these value, all these things. Like, so moment of rectangular section about x axis is simply BD cube by 12, whereas if you take about y axis, it is simply dB cube by 12. Again, moment of inertia about the uh, about the AB axis is simply you can take as BD cube by 3. Next, moment of inertia of a triangle about x axis is it is simply BH cube by 36, whereas moment of inertia about AB axis is BH cube by 12. Next, circle. So if I take a circle, the moment of inertia about Ixx is simply is equal to Iyy. Now that would be equal to pi d power 4 by 64. And we have also discussed that for a semicircle, uh, if you take Ixx, then it is 0.11 r to the power of 4. Next, Iyy is equal to Iab is equal to, it is simply what? It is nothing but pi r power 4 by 8 or pi d square by 128. So like this, we'll go on doing the calculations, right? So in uh, tomorrow's class we'll be discussing so few problems about this, and for a quarter circle or for a quadrant it is Ixx is equal to Iyy is equal to, simply we'll take uh, 0.055 r to the power of 4, and IAB is equal to pi r power 4 by 16. Okay, so this is how we calculate the values for everything. Okay, so in the next class we'll be discussing about the moment of inertias of the angle section, and we'll discuss about the moment of inertia of the non-symmetric and symmetric sections. Okay, so that is all for today. And also we'll discuss for a z section, and for a channel section, and for I section and all, and we'll solve a few problems on that, and we'll try to find the radius of gyrations and all for everything. Okay, this is all what we'll be doing in tomorrow's class. And this is all for today, and in this class we have also discussed the theorem of parallel axis, that is the moment of inertia about the moment of inertia about any plane figure can be taken as about an axis is equal to sum of the moment of inertias of uh, about the centroidal axis and the product of area and the square of the distance. Next, theorem of perpendicular axis it states that if Ixx and Iyy are the moment of inertia of plane sections, then then about the mutual perpendicular axis, then you can simply take as the moment of inertia about Izz is equal to Ixx plus Iyy.